It's a pleasure to have Rutger here, who will talk about squaring relations from on-shell constraints.
Right, so first of all, let me thank the organizers for having me. It's fun to be in Cambridge. Now I realize that this is getting late, so this is going to be the most low-tech talk of the entire week. I've seen very many impressive high-tech things. I can only do stupid things. So let me show you what I have. I'm going to talk about quite general squaring relations. Now, you've been hearing about squaring relations basically all day already. It's basically the idea that you can write, say, a graviton scattering amplitude as a sum over squares of things you build out of gluon amplitudes. Just in general, there's many relations of this type known, as reviewed by Radu in his talk and by John Joseph. I want to find out why this works. Right, now up to now, there's been two schools of thought on why this works. So the one school of thought says these things work because of string theory. In string theory, in most string theories we know how to solve or know how to analyze. The closed string vertex operator splits into a left and a right sector, and basically this thing, through some magic in manipulating the integrals, gives you a relation between amplitudes with gravitons as sums over squares of amplitudes of gluons. It doesn't really tell you yet what these relations look like, but this is the fact which makes the clock tick. Right, the other school of thought says, no, you don't need any string theory, you can just stick to field theory, and you talk about color kinematic duality, and you've seen today many talks about this. Right, now to my mind, the state of the field can be summarized by this particular image. We're in the hunter-gatherer stage of development. We're trying to find examples and trying to make things work. I should say, this holds especially at loop level, not so much at tree level, and also at loop level there's signs of farming appearing, and we're getting somewhere. Right, but still, there's some questions you could ask: is what are we really studying? Where does it come from? Why does it work? And how far can it go? So these are the types of questions I want to address today. And don't worry, I actually have an answer, but not at loop level, but at tree level. Right. So what I want to do is I want to derive these squaring relations from first principles. I want to find a set of principles and derive the squaring relations. This is a type of question I like a lot, actually. So the question is, which constraints do you have to impose on an amplitude such that the answer is uniquely what you would like it to be? Or more generically, what kind of scattering amplitudes are allowed by unitarity, locality, and make a list of your favorite constraints. Right, so I'm going to do the same thing, but then I'm going to take a look at squaring relations. Right, so when I say first principles, I have to specify to you what my principles are. So here are my principles, and let me immediately come clean and say I'm not going to cover the whole space of scattering amplitudes. I'm going to make some specific choices. I'll talk about tree-level things. I'll specify what I mean by tree-level in a second. I'll only study massless boson scattering. I will be d-dimensional. I will not specify specific dimensions. And I'll study parity-even amplitudes. So this is, to my mind, a reasonable set of restrictions, and you can loosen any one of these and start asking me, why didn't you do that? I just simply didn't do it. So, right. So what do we need? Any theory. Let me give you my set of principles, and then you just see if your favorite example fits into the set. Right. So I have massless particles. So what is a massless particle? It's something which has an on-shell momentum which squares to 0, and is specified by some irreducible representation of the little group. I have Poincare symmetry, so I have momentum conservation, and Poincare symmetry also means that since scattering amplitudes are scalars, all the indices have to be contracted with metrics. I'm looking only at parity-even things. That means I will not allow the epsilon symbol, also because I want to be dimension agnostic. I don't want to get to a specific set of dimensions. When I say tree level, what I mean is I'm just going to specify rational functions. I don't want to admit any logs or anything else, just rational things. Right. I'll take locality and unitarity, but I'll actually not use them that much. When I say locality and unitarity, what I mean is you make some assumption on what kind of poles you get. This is not going to be very important for my talk, but it is something you can input. And of course, there's Boels symmetry. if I take the quantum numbers of any of my legs, say the momenta and color or whatever quantum numbers you have, and I start interchanging them, my amplitude has to be symmetric. Right, so this is my set of principles. I should say for gluons, people studied exactly this set of principles in 2013, and they got some interesting answers, and I'll get to the interesting answers in a second.
What do you mean by principle? Why is it not just quantum physics?
Well, I want to give you a definite set of the assumptions I'm going to make. These are the assumptions I'm going to make, which I think are all perfectly reasonable, and I'm going to derive whatever you can get from it. Right? Okay, so I need to be very specific about what I mean and what I use. So for every external massless particle, I have an on-shell momentum and an irreducible representation. These I build out of tensor products of my polarization vectors, which obey two constraints, right? So one is transversality. The polarization vectors are orthogonal to the momentum in that particular leg. And the other one is called on-shell gauge invariance. If I take a polarization vector, any polarization vector out of this tensor product, and I replace it by its momentum, I want scattering amplitudes to vanish. The first one is well, I should say you actually need two constraints because you have to get down from a d-dimensional vector to a d-2-dimensional vector. So this is perfectly reasonable. The other thing I want to stress is that this particular constraint is basically the linearized field equation. But a better way of saying it is a consequence of Noether's second theorem. It's just a consequence of the fact that you have a gauge symmetry. So basically, the only input I take here, there is a gauge symmetry. Right. A scattering amplitude is multilinear in external polarizations, as you all very well know, and you have to choose the meta content, and for this talk, it's either going to be a gluon or a graviton, basically. So you can start studying higher spin examples, and I can tell you interesting things about it, but for this talk, I'm not going to do it.
But you're not studying scalars.
I could study scalars. Well, you can always study scalars by doing a dimensional reduction of some type, and those theories are all included. Scalars, from my point of view, are going to be trivial extensions of what I'm going to tell you. Right. So let me work out Poincare symmetry a little bit more. The simplest building blocks I can make out of momenta are basically momenta contracted into each other. But the set of all momenta contracted into each other is overcomplete, so you need a minimal set. Now, many people here in the audience will know minimal sets, right? So the simplest one is for 4 points, you have two Mandelstam invariants you can pick, and you can construct all the other inner products out of these two. At 5 points, there's a set of 5 Mandelstam invariants, and it's, well, Oliver once taught me you can pick them to be cyclic, which is something nice if you have problems with cyclic symmetry. And actually at 6 points, there's also a set which is cyclic, so you take the same type of things, but now you have to add these three guys, and you can go on like this. So there is a solution to this problem. You simply solve it in terms of a minimal number of Mandelstam invariants. So in general, you just keep on going. You start adding these cyclic orbits of things, and you have to end somewhere. And I checked explicitly up to 10 points that this is a complete set. It's not because I can't check it for anything higher, but simply because I ran out of, well, energy to press Shift Enter. Right. So the main idea I'm going to tell you today is that I'm going to treat scattering amplitudes as vectors. And this is an important thing. So they're vectors because they must be multilinear in the polarization tensors, right? So these polarization tensors, they must contract into some other tensor, which I can build out of only a few building blocks. So what are my building blocks? I can contract a given polarization vector with another polarization vector by using a metric, or I can contract into one of the other momenta, right? So far, so good. Right. And actually, you can stratify these terms you can have by counting how many metric contractions between external polarization vectors you have. This is actually a very nice measure to have, because you know that in Yang-Mills theory, all the terms in a tree-level amplitude have at least one metric contraction, and all the terms in an Einstein-Hilbert amplitude have at least two metric contractions. Right? This is something which you can simply see directly from perturbation theory. There's other ways of showing this as well. But I'll get to those in a second. Right, I have momentum conservation. That means from this set of momenta, I can always eliminate one by momentum conservation. And I need to demand transversality. So if terms which are of this type, I'll set to 0. The only subtle thing is, if I eliminate this thing from my set, I have to make sure that I still take the transversality condition for the last polarization vector. This is just a technical detail. Right, so what I've got left is a combination of objects of this type. So there are contractions of polarization vectors and momenta, and this is actually what it looks like in my Mathematica code, times coefficients. So a scattering amplitude for me at the moment is a linear combination of terms of this type, right? I've solved transversality, I've solved momentum conservation, I'm just going to solve all the constraints in my set. Right, so this is a vector space. So every amplitude has a unique representation in this particular vector space. I've made some choices, I've chosen a momentum here, but that's it, right? It's not a unique vector space, but every other vector space is just a transformation of this one. Right, so let's look at gluons, right? If you have 4 gluons and you have at least one metric, then there's 27 terms of this type you can create. And as you can see, this increases very, very fast. And of course, John Joseph will now immediately point out that this is factorial growth staring you in the face, which is true. There's very, very many terms. And you might now think that you're dead in the water. It turns out that you're not dead in the water, and the number of things which are actually allowed by the symmetries is very much less. So if you solve on-shell gauge invariance, actually the number of terms is dramatically less. It's just you solve you just solve a whole linear set of equations. You find that the solution space is very small. And if you check this, you'll see that if you have at least one metric contraction, the number of solutions you get is exactly n-3 factorial for up to 7 points. Yes?
Maybe I missed it, but did you have any constraints on the mass dimension of the spaces?
No. No, I allow coefficients which are arbitrary functions of the Mandelstam invariance. I mean, you want something which is homogeneous in mass dimension, but that's kind of trivial, I guess.
Okay.
Yeah, but in principle, anything.
Oh, anything.
Anything. So I don't put any constraints. I just put my list of constraints. I ask Mathematica simply for the null space of the resulting set. Right. So this is a nice number. It tells you that for say 4 points, there's only one vector which can solve on-shell gauge invariance, which means that every other amplitude you can express as a function of this one vector.
Sorry, but you're looking at the polynomial, right? What about the poles, etc.?
So if you have a given amplitude, you can always express it in terms of a chosen basis times a function of Mandelstam invariance, which can have poles and I mean, they're rational functions because this is something I assumed, but this is the only assumption you have to make. This is just always true. Let me give you an example in a second. Right, so these solutions are up to overall functions, so I can always take a solution multiplied by any function of the Mandelstam invariance, that's also a solution to the constraints, right? And I can take linear combinations of solutions. Right, I should say these numbers alone explain why BCJ relations exist for generic gluon amplitudes, as long as you satisfy the constraint that you have at least one metric. And for Yang-Mills, this definitely holds. In string, it also holds. It doesn't tell you the form of the relations in general, it just tells you that there will be relations in general. Right, I should say that the analysis for gluons with at least one metric is actually contained in that paper. And the point of the paper was to show that for string theory, the BCJ basis is actually a proper basis for string amplitudes in general. It explains why you can write a string amplitude that way, as long as you prove in a string that you need at least one metric contraction. Right. So let me show you that you can actually use this to actually compute stuff. This is not just something you observe. So if you take a set of gluon amplitudes, you can construct these unique vectors times the elements of my ansatz. And if you have a set of these gluon amplitudes, you can actually create a matrix. M by number of ansatz elements. I should say if you're at 6 points, for instance, and you take, say, 30 of these amplitudes, then this is a 30 by 4,500 matrix. And you can simply ask for the null space of that matrix, and that will give you the relations between all the different amplitudes. And since you have a matrix which is grossly overdetermined, it's actually, in most cases, you can just truncate to a much smaller matrix and solve the problem. You just get the null vectors pretty simply. Actually, if you do this in Mathematica, if you take your choice of BCJ basis to be the first few vectors, and you pick any other vectors to complete this, the output is actually the complete basis map. So it just maps any vector onto the basis. It gives you all the BCDA relations. This is very similar to what you would do in a Laporte type algorithm. Right, so one thing I did is just construct six-point gluon amplitudes and check that they are all independent, which is just something you know. But it also shows you that you can express any set of amplitudes, gluon amplitudes, which satisfy the metric counting criterion in terms of this BCDA basis. In string theory, field theory, any theory which satisfies the same principles. Right, you can actually do more. You can actually compute stuff as well this way. So let's compute a 6-point gluon amplitude. You can just solve the on-shell constraints. You get 6 solutions, right? Mathematica can do this. But the mass dimension of these solutions is actually way too high. Also, it contains very many poles in general. So you need to find a linear combination of your 6 solutions which satisfies additional criteria you might want to have. So for instance, if you want to have a color-ordered amplitude with a particular color order, you want it to be cyclic. So one thing you can do is you can take your 6 solutions and you sum over cyclic orbits and you multiply by the allowed maximal poles to make the mass dimension fit. Then you get 84 different types of vector, which are all cyclic, but they are related. So you're looking for a rational number vector which combines these into a scattering amplitude. And one interesting thing is you can just use integer numerics to do stuff like this. So if you demand that you get the leading BCFW shift relation correct, you get a unique answer. You just need to find the z times metric type of thing, and that fixes the complete amplitude. There's only one solution, and it's unique. And it is the 6-point Yang-Mills amplitude. I should say, this is not the way you want to calculate in general. It introduces way too many degrees of freedom, but it does work. You can actually find gluon amplitudes this way. I think you get the same result if you impose that you only have simple poles in allowed channels, but this I didn't check yet. Right, so what about gravitons? Right, so now we scale up. Let's do gravitons. I've only been able to solve the 4-point case. The problem is that the tensor structures get very, very big very quickly. So even at 4 points, the number of terms in your ansatz, if you have more than 2 metrics, or 2 or more metrics, is already in the 5,000 element range. This is something my laptop can do, but 5 points my laptop certainly cannot do, and maybe even the big computers cannot do it. Right, so when I say gravitons, is I take something which is left-right symmetric, and I drop all the terms which only contribute to the trace factors. I actually did not subtract off the trace directly, but the answers I get are actually independent of this. I can tell you why they're independent. Right, so if you impose on-shell gauge invariance, the number of allowed vectors decreases dramatically. And for instance, if you have 2 or more metrics, there's only one solution to the on-shell constraints. And this solution is indeed proportional to the Einstein-Hilbert amplitude. Right. Now an observation. If you give me any solution for gluons of this type, and you give me 2 of them, I have a solution of gravity. This is basically the same as what Radu said this morning. If you have 2 things which obey on-shell gauge invariance, then the product will also obey on-shell gauge invariance, but now for gravity. Right. So I can always take my 2 solutions with 1 metric out of my Yang-Mills set, they are unique, and create a unique solution up to functions of Mandelstam invariance, which is the Einstein-Hilbert answer. In other words, I've just told you why the KLT relation works. I've actually told you why the KLT relation works in Yang-Mills theory, in string theory, in any theory. In any theory which obeys my set of constraints, you will get a KLT type relation. Always. There's nothing mysterious here. You don't need a kinematic algebra, you don't need a string theory. The only thing you need is on-shell gauge invariance. It's simply on-shell gauge invariance which makes everything tick. Right. I should say there's some magic hidden in this number. And I'll show you what the magic is in that number. Right. So let me show you what the magic is. Let me go back to gluons, 4-point amplitudes, just gluon amplitudes. This thing is the Yang-Mills amplitude, the 4-point Yang-Mills amplitude. But now I want to see what these are. What are the extra ones? Right. So if you look at this amplitude, it's very well known that the Yang-Mills amplitude can be written as something local and something which is just symmetric times 1 over st, right? So you might want to see what happens to these. Can you write these in a similar type form? You would expect that you can write them as some local form. You can always write it as a local form. You just multiply by all inverse pole factors. And it turns out that these 10 split into 7 plus 3. Why is it 7 plus 3? 7 of them you can take to be completely both symmetrizable. They're completely symmetric. These 3 are anti-symmetric in 3 legs. There's some other choices you can make, but you can definitely not write these as completely symmetric amplitudes. That's impossible. You can show it's impossible. There's no function of Mandel's you can take to multiply with this to make it completely both symmetric. Right. So the minimal mass dimension, at least if you factor out completely symmetric functions of Mandel's invariance, seems to be 0, 4, 6, 6, 8, 10, and 10. I've got no idea why you get these, but this is what you get. And these have pretty high mass dimension. So the reason why these are actually separate sets is that the only polynomial which is completely anti-symmetric in 3 legs is actually anti-symmetric in the exchange of 4 legs. And that polynomial is unique. And that you can use to show that you can never write these as that. I should say, if you look at these scattering amplitudes, the thing which would fit to them would be some FABC times the U1 factor. That would fit perfectly to the symmetry structure. Right. Now this is fun because this I can use to square stuff. If I now take a Yang-Mills amplitude, which is completely symmetric, I can only take one of these amplitudes to make a both symmetric graviton amplitude. Right? I cannot take a Yang-Mills amplitude and one of these set, because if it then both symmetrize the result, I will get 0. Right. So for gravitons, I had these solutions. These, if you apply both symmetry to them, so 3 of them drop out here, and I can create 1 and 7 from gauge theory squares. Now 8 is not 7. That means that there is a graviton amplitude for gravitons, which you cannot write as a sum over squares of Yang-Mills amplitudes. There's a graviton amplitude, a 4-point graviton amplitude, which does not obey color kinematic duality. It will not appear in string theory, and it is something separate. I should say there's a couple of loopholes here, so let me mention a few of them I know. You can't do this in a dimension agnostic way, but as soon as you go to a particular set of dimensions, I think there's ways around it. So let me mention 3. So one of them is you take 2 parity odd amplitudes for the Yang-Mills amplitudes, and you square them. Now that, of course, applies having Levi-Civita symbols, so that doesn't work in any dimension. You can go to 4D special kinematics that imposes additional relations. And it could be that there's a problem because I've only imposed symmetry in left-right sectors, but I didn't really subtract off the trace correctly. That subtracting of the trace always introduces a 1 over d factor, so certainly that will not give you something which decouples for any dimension. Right. So if you want to give this a name, this is an amplitude in the string swampland. It's an amplitude which you cannot explain as the low energy limit of any string theory. Because string theory always, as far as I know at least, implies factorizing vertex algebras. Right. I'm slowly getting to the end of my talk, so let me tell you a little bit about what this one metric constraint means. You might think, and this is actually what Medina and Barrero originally conjectured, which turns out to be false, is that supersymmetry implies that you have always at least one metric contraction. And this might be true for maximal supersymmetry, but it's certainly not true for less supersymmetry. So let me tell you why you might think this, or at least why I thought this was true. So if you go to 4 dimensions, you can show that helicity equal and one helicity unequal amplitudes vanish in any supersymmetric gauge theory, right? Now there is a gauge you can pick for which 2 polarization factors from different legs are orthogonal. So that means if you take any of these scattering amplitudes, so for instance for all helicities equal, that the only terms which contribute to something like this are the terms without any metric contractions, right? So if you have a scattering amplitude which always has at least one metric contractions, these amplitudes are guaranteed to vanish. But unfortunately, the implication does not go the other way. So there's an explicit counterexample to saying that supersymmetry implies that you always have at least one single metric contraction, and it's a 6-dimensional n 1,0 amplitude found in that paper. So what happens there is something special. Is if you take all helicities to be equal, so you take all polarization vectors to be of this type. By the way, this is a very neat way of imposing all plus helicity in a vector type way without using spin helicity. If you impose 4-dimensional special kinematics, then any set of 5 vectors is not going to be linearly independent. If you impose this constraint on the scattering amplitude, on the scattering amplitudes, you can show that there are at least 2 combinations of terms which involve this type of structure, which have vanishing all plus amplitudes. These are terms which are in principle supersymmetrizable, and by the fact that this thing appeared in explicit supersymmetric computation, you know that you're going to find these terms. Right. So this metric counting, my gut feeling is that for maximal supersymmetry, this is true. For less than maximal supersymmetry, it's certainly not true. Right. So what have we learned? The thing I've learned is that on-shell gauge invariance is a very, very powerful constraint. In other words, I'm telling you that local gauge symmetry is a very, very powerful constraint. This is something which we all should know, and just see yet again. The KLT relations, any squaring relation, KLT-like squaring relation, is kinematic in origin, at least for 4 points, and since it works at 4 points, the usual thing is it works at any number of points. The other thing I've learned is that not all gravitational theories square. I found an explicit counterexample to that claim. It's a very contrived counterexample, if you like. If you restrict yourself to just Einstein-Hilbert, you're fine, don't worry. But if you want to find all n equals 2 supergravities, this might be a little bit of a stick in your bicycle wheel. The thing I've learned, and this is the thing which makes all this stick, is you need to do linear algebra, but you need to do it fast, because all the matrices involved are very big, so you need to program quite a bit. But it's something you could do very, very quickly. Right, so the thing to do is to just gather more data. I'm also a hunter-gatherer still, so there's all kinds of things you could be thinking about. Here's a non-exhaustive list. You can try to go to loops by factoring out tree-level type factors out of your loop amplitude. This is bound to work, almost. And you can try to find a better basis for string amplitudes. For instance, a cyclic basis would be very, very nice to have. And I can tell you a little bit about that if you would like to, but you can probably ask a better question than I can think of. Thank you.
Yeah, at loop level, the integrands are not gauge invariant, typically, at least if you just write them down in this sort of...
No, but after integration over the loop momenta, you would expect that you should be able to express your amplitude in terms of these building blocks. Always. There's no other building blocks. So after integration, you should
not be a rational function.
Sorry?
Not be a rational function.
No, then you can. I mean, what I would hope for is that you can express it in terms of these building blocks times scalar integrals. But that's not guaranteed, and I can tell you what. I mean, I can show you why it's not guaranteed. But for n equals 4, this is known to work at least for 4 points, right? 5 points, maybe. Well, sort of. 6 points, it gets harder. Yeah, I don't think that's completely out of the question. Hero.
In 4D, did you try to write your answer in terms of spinners?
I could. I mean, the Yang-Mills amplitude is easy. I didn't try the other ones. If you impose 4-dimensional special kinematics, you might find more solutions than I found here. So I solved basically for null spaces of just generic matrices. In 4 dimensions, you might find more solutions. This I didn't check for. I mean, it would be interesting.
Coming back to Eduardo's question, your amplitudes that do not square,
Yes.
are they all of the form epsilon dot t to some power? Or is that
They all contain terms of that type, yeah. And there's other terms in there as well, because on-shell gauge invariance tends to relate terms with different numbers of metrics. But there's always going to be a part in there which has this epsilon dot k to the power of 8 type terms.
In the bosonic and reduced string, you find this kind of terms coming, and they definitely correspond to some higher derivative.
Yeah, so I should say I have 6 solutions of this type, and one linear combination of them is not of the form you can get from a string. So I still have a space of 5 to capture your answer. So it's, I mean,
But how do you know the space of things you can get from a string?
because look, all the constraints I listed are obeyed by the twisted string. At least I hope, because otherwise it would be not on-show gauge invariance, for instance.
So like the amplitude string with a negative non-state or this, I mean on the one side.
Those I don't care about. As long as you have, as long as you satisfy the list of constraints I put, which includes on-show gauge invariance, all the things the twisted string also
You
obeys.
expect unitarity at loop level.
Yes, so unitarity plays a little bit of a, that only plays a role once you really start massaging an answer into a form you would like, with certain pole structure or whatnot. But just the number of solutions I didn't use unitarity to get that, I just solved a matrix system. So any theory which obeys my set of constraints will have that answer, and I didn't use locality or unitarity to get there. Yeah, I mean, in a specific case, I can give you a map.
Amplitude in a non-unitary theory.
You could include amplitudes in non-unitary theories as well. Yes. For instance, if you try to do a 4-spin-3 scattering, you find an amplitude which needs higher order poles to work for a 4-point amplitude.
For the bosonic string, the 4-point amplitude will realize 4 of these linear combinations.
Yeah, I would expect something like that. Yeah. So if you would find more than let's see, more than 5 of them, I would expect that there is a relation between them, with coefficients which are functions of Mendelssohn invariance in alpha prime.
Okay, then I'll make 4 of them explicit on Friday morning.
Sorry?
And I'll make 4 of them explicit on Friday morning.
Okay.
Do you have a guess? Do you have a guess for an action that produces this non-factorizable amplitude?
No. So that is a good question in general. So I should say you can look the space of things which satisfy on-shell gauge invariance. One thing which definitely satisfies on-shell gauge invariance is, for instance, the linearized version of f. So just the f mu nu, just the gauge fields. The tensor, right? So the linearized version has on-shell gauge invariance, and in gravity you can take the linearized Riemann tensor. That works. So Oliver gave me some of these things, and I can relate to that basis, and that might make it easier to find where these things came from. But the map is going to be, I mean, it's always going to be a little bit tricky, because the usual thing is that the off-shell effective action is going to be a lot more floppy than the on-shell forms I have here. But look, I haven't tried yet.
The reason I'm asking is that the power counting that you are listing, that everything comes as k dot epsilon, suggests that you have more than two derivatives per vertex.
Yeah,
That's
so
not
that's
a lot now.
no. So that's, I mean, that's something you could work out, right? So the mass dimension you could work out, and then you could play around a bit. Yeah, I'm quite sure that you could find it. But there's one problem you have, is that you can always add terms which are squares of things to this form to make it simpler or more complicated, whatever. So there is a little bit, yeah, it's not a completely straightforward computation, I would say. But it's doable, definitely.
Is the n-3 factorial somehow related to the solution to the scattering?
I don't know. So in this language, you would say that after solving the on-shell constraints, the number of solutions for for gluon amplitudes with at least one metric contraction is n-3 factorial, right? And Medina and Barrero conjectured that to be the case, but they didn't go beyond 7 points. I should say I also didn't go beyond 7 points. It's a quite reasonable assumption, but it would have to be proved. I think it can be proven, but I really haven't tried.
What I'm asking is it related to the fact that that's the number of solutions to the scattering?
Yeah, so I should say, to my mind, the scattering equations and CHY representation are just a different way of solving the on-shell constraint. I mean, That's my personal point of view.
Well, not really, because you can do it for a scalar theory. You don't have to with the gauge invariance for CH1.
Well, if I introduce scalars, I also don't need to use gauge invariance for those legs as well. I mean, I can do the same game with introducing scalars. It would make it easier. Because the problem I have is that the number of tensors you can create grows very, very fast. But scalars are basically for free. Right? So, I mean, if you want me to give you some numbers, I can probably get them very quickly. Look, to my mind, the CSY representation, color kinematic duality, the KLT relations and string theory, all those things are just expressions of the same basic kinematic fact that onshore gauge invariance is very, very restrictive.
What I'm saying is you can do CHY for just scalars where there is no gauge invariance.
Yes, so in that case, I think you're just, I mean, you're counting things.
The order of that CHY is coming just from the scalar theory. All the gauge stuff is just coming in from the vacuum.
Look, so those theories, I mean, for me, there would be only one solution. This is basically a constant times a function of Mendelssohn invariance. So that type of theory from this point of view is trivial.
And you don't have n minus 3, you have 1.
Yes, there the answer will be 1.
Luis, if you want to find another n-3 factorial in CHY, maybe it's the number of Park-Taylors. If you take the Pfaffian, shape it, and simplify all the Park-Taylors that you get using scattering equations and partial fraction, then you will land on n-3 factorial Park-Taylors. Then you can ask Rutger to give you the kinematic companions of this.
Right. That's not Campbell's solution. That's Campbell.
Maybe maybe a bridge using KLT orthogonality? Park-Taylors and solutions? Or is this unrelated?
Well, if you really want n-3 factorial, one thing you could do is I now just did kinematics, but then you would do the same game, but then you include FABCs everywhere. But that's true. That would be a trivial game.
You don't need, well, I'm sorry, maybe I didn't understand. You don't really need the group here. Right, you can go.
Yeah.
Yeah, I just wanted to check, so the Mendelssohn you're using, so it's just the basic counting of, like, you have STU at 4 point, but then you restrict like a momentum conservation to S and T
Yes.
and 5 point, but you don't take into account any grand determinant constraint.
No, so those would, I mean, if you, as I said, I'm doing this in a dimension agnostic way. If you go to specific set of dimensions, then you get the gram determinant problem, I would say.
Do you know if that makes any difference to?
So I know there's one example where you need the gram determinant basically to make a scattering amplitude not vanish. But this specific amplitude in a 6-dimensional 1,0 theory. I don't know in general. I mean, in general, I would actually put. Well, there's other ways of imposing 4-dimensional kinematics, and then I would use those. Actually, for just counting solutions, you can take integer numeric solutions in 4 dimensions. That would be much faster.
So in general, like the quantum field theory, you can add arbitrary interaction term in Lagrangians.
Yes.
So, but you said the solutions view, for example, is 4 point is 1, and the 5 point like the 2. How this freedom in Lagrangians showing you like the
Okay, so say you take blue, right? So there's a couple of rules. So the extra terms you add have to be gauge invariant, right? Then if you compute the scattering amplitude, the number of independent solutions is not 1. The number is 10, right? So only one of them has a single metric contraction and more things, and the other ones are all of the type epsilon.k to the power 4. So these extra terms are all going to contribute to those amplitudes or to the gluon factor, one of them. I mean, the mass dimension counting I showed you was for local completely symmetric amplitudes. Local completely symmetric amplitudes, and those probably correspond almost 1-to-1 to terms in the effective action. But I didn't make the map to the effective action precise. It would be interesting to do. I mean, there's a finite number of hours in the day.
So basically, what I said is under your requirement, some like term cannot be added arbitrarily. For example, F4 term, F6 term Young means we cannot add.
Well, no. So you can add them, right? The only thing I'm telling you is that if you add them, they would show up in my basis as specific coefficients. But there's only a finite number of different tensor structures which can appear. So even if you add, I don't know, d to the 800 f to the 4, right? That would appear as some linear combination of these 10 solutions with very high powers of Mendel sums in front of them. You can always relate them to a sum over simpler gluon
But the
amplitudes.
fixed solution itself is not fixed. It can be changed with different theory.
Yes, yes. So, for me, these all show up as Mendel sums in front of stuff. Just think about the string amplitude, for instance, right? So the superstring amplitude is a Fininciano type factor times the 3 amplitude. Then I can ask the same question. And the answer is, in any order in alpha prime expansion of the prefactor, you can map that to certain terms in effective action, but they all are proportional to the Yang-Mills tree.
I see.
If there are no further questions, let's thank Rutger again.